So for part A,
In order to kind of solve these equations that we're given to then get an answer to our previous
problem, first
we can do is that we can just trivially set x4 and x5 to be 0 since like those variables don't exist in our original problem. So that would kind of give us the reduced equations that I have written down for part A. And with having those reduced equations, it's clear to see that we can then turn this into kind of a system of solving the system of equations. And after doing so, the answers that I got for each of the variables previously were x1 equals 5 over 3, x2 equals 0, and x3 equals 3. And that gave us kind of
total value of 17 for Z. And then so for part B, we can just use kind of the techniques that we've learned in class and through the book.
About how to turn polynomial problems into dual problems. And doing so, we can, of course,
change our
proven reductive functions become our new kind of constraint. Right hand side of our constraints. The right hand side of our current constraints turn to new coefficients for the dual problem, and then of course we have to and then make like the correct left hand sides for the constraints. In part C, after now having a dual problem, what we want to do is solve it graphically so we can graph all the different equations. Kind of gives the 3 lines we see, and since these constraints are greater than or equal to, the feasible bound region will be kind of above these lines that we graph. So knowing that, we can kind of solve for like what the max would be by trying to find the corner point feasible solutions, and seeing which of them is maxed out. So, and then kind of based off of like doing that, I found that this 1 over 5 3 over 5 kind of was the answer that would kind of minimize that for this dual problem. See, for part D, we can
take our previous answer from the last section and compare it to
the new constraints, and when doing that, we can see that not all of our constraints are met. Specifically, I think constraint 3 does not hold, so
kind of like our previous answer is invalid, and then kind of using that like
knowledge, we can set up these matrices for part E
in order to get the correct coefficients for x2, which are negative 1 over 3, 4, and 4 over 5. So then for F, kind of using similar logic as we used in D, we can plug in again our optimal solution that we found, and we'll find that again, like not all of our constraints are met. So this constraint 4 does not hold, so our previous solution again is not valid. So again, we have to set up matrices similar to what we did in part E, and in order to get the correct coefficients for x nu, which turned out to be 1 over 3 and 1 over 5. So for number 4, as we learned like in class in the book, the branch and bound technique is kind of one of the ways to approach a mixed integer programming problem. So for this problem specifically, what we kind of needed to achieve is to initially solve and get initial solution. So kind of like what is the initial optimal solution
for this problem without the integer constraints, and work from there. So as you can see at the bottom of the page, kind of like the
actual solutions themselves are worked out
in Excel.
Or there's extra work in
Excel, but once you kind of get these solutions, so it is then on us to like kind of upper bound and lower bound the problem. So for the first solution, as we see, our first variable is a 2.2.13. So we need to upper bound and lower bound that. So ceiling and floor that. So upper bound would be 3, and our lower bound's 2. So then so kind of working down the upper bound tree now.
We can see that our next variable is 0, which is already an
integer, so we don't necessarily need to worry about that one. And then our third variable, which also needs to be an integer, is not. So we need upper bound and lower bound that solution again. So moving further down the tree, our upper bound solution 306, and then into like whatever x4 would be, like based upon like kind of the equations and like constraints functions that we're given, like that would just move us into an infeasible range. So we don't really need to again further keep exploring that path. And then our lower bound solution did going to 5, leaves us in like with a valid solution. So we can go ahead and use that, and using like those constraints and getting 0.5 is like kind of like the optimal value like with those first 3 integer constraints. And based on the kind of the way our problem was constrained, we know that x4 does not need to hold as an integer. It just needs to be positive, which it is here, so we can kind of stop a branch or bound on that side of the tree and kind of get maxed out. I think we got that level was z being 195, because the other the upper solution is infeasible. Just kind of moving back up now to the lower solution of our initial solution. So where our x1 is now lower bounded to 2. We can see again that our x3 is also not an integer in this case, so we need to upper bound and lower bound x3. So that gives us 2 solutions, one where x3 is 4, one x3 is 3. We can see that both give us x4s that would meet the constraints of being greater than or equal 0. In the Excel, it's clear, because we work it out, that each of these kind of answers, and all of them across everything we've worked out, meets all the constraints. So then, and then down this path, the largest z value seen as 193.34. So now it's up. So based on like all the different paths we can follow, it's clear that that the solution where we have x1 is 3, x2 is 0, x3 is 5, and x4 is 0.5 is the optimal solution, because it kind of gives us that maxed out z value and maximizes our objective function. So yeah, so for number 6, I was able to derive the KKT conditions as follows. So, the conditions being pretty clear, these 4 conditions, and then also the constraints. Then once these were derived, we could then start to solve for an optimal solution by using these conditions. So kind of the first order of business there was creating relationships between between the x1 and x2 variables and u, which we were able to do. And once that was done, we could then plug in plug in for x1 and x2, like the u values that we were able to solve for, and everything canceled out to kind of give us a u of 1/2. So then taking that u 1/2, we're then able to plug it back into the equation from before, and that can give us an optimal solution of x1 being 3/4 and x2 being 5/4. For part B, we then needed to create the LP, the linear programming problem, that would work for the modified simplex method. So doing is kind of what I did, taking the different decision variables, different constraints, and be able to come up with this LP, which we could then apply the modified simplex method to. That kind of then moves us on to part C. So in part C, we
actually apply the modified simplex method that we're trying to set up for, but we could still verify our initial solution by plugging in the answer we got from our KKT derivations. So doing so, plugging into all different constraints, it was clear to see that the constraints at every level continue to hold. And since they all held, we could then say, still be confident that our solution was optimal since every constraint was met. In part D, now you're actually tasked with actually applying the modified simplex method to our LP. So, just had to set up the tableaus. There were 3 iterations, and working through these iterations, we ended up, with the same solution as what we had from part A and KKT. So again, just showing that 304504 is the optimal solution. And then moving into part E, we again wanted to try solving a different way. This time we used dynamic programming. So there were 2 stages. On each stage, we had set up like a maximization equation. And then to essentially solve those equations, we had to take derivatives and account for a bunch of different cases for what that decision variable would be would end up being, and bounding that decision variable based on what we wanted, like the output of like the equations to be. Working through all that math, we got a result of x1 coming out to being 3/4. So taking 3/4 and plugging that into our constraints, we were able to then solve that x2 again was 5/4, which kind of again affirms what we found both from part D using the modified simplex method, from part C just plugging into constraints, and from part A using KKT conditions. And in part F, solving via quadratic programming, or as something that I laid out in the Excel sheet that's attached to this final. And again, kind of resulting in the same result as we saw